Imagine something so vast and powerful that it shapes the very galaxies we see in the night sky, yet remains completely invisible to our eyes. This isn't science fiction. It's the reality of dark matter halos, the mysterious cosmic scaffolding that holds the universe together. These colossal structures, stretching hundreds of thousands of light years across, are the unseen architects of the cosmos, bending space and guiding the dance of stars. But here's the catch: despite their immense influence, we've never directly observed them. They don't emit light, reflect it, or interact with the ordinary matter we're made of. They're ghosts in the machinery of the universe, and their secrets are some of the most tantalizing puzzles in modern astrophysics. What makes dark matter halos so fascinating isn't just their invisibility, it's the sheer scale of their influence. Without them, galaxies would fly apart, and the universe as we know it wouldn't exist. Yet, for all their importance, we still don't fully understand what they're made of, how they form, or why they behave the way they do. From their bizarre gravitational fingerprints to the way they warp the fabric of spacetime, these halos defy our expectations at every turn, and that's just the beginning. Hidden within their shadowy depths lie at least 25 mind-bending mysteries, each one more perplexing than the last. Some hint at entirely new laws of physics, while others challenge our very understanding of reality. This is the story of those mysteries, a journey into the heart of the cosmic unknown. We'll explore the strange, the unexplained, and the downright unsettling questions that keep scientists awake at night. How can something so invisible shape the visible universe so profoundly? Why do these halos seem to ignore the rules we thought governed matter, and what clues might they hold about the fate of everything? Buckle up, because we're about to dive into the enigma of dark matter halos, peeling back the layers of one of the universe's greatest riddles. By the end, you'll never look at the night sky the same way again. Think about holding a map of the cosmos in your hands, one where only 5% of the landmarks are actually marked. The rest, blank spaces, invisible to every telescope and sensor we've ever built. That's the staggering reality of dark matter halos. These cosmic giants make up roughly 85% of all matter in the universe, outweighing everything we can see: stars, planets, even galaxies, by a ratio of 5-to-1. Yet they leave no trace in the electromagnetic spectrum. No light, no heat, no radiation. If it weren't for one crucial clue, we might never have guessed they existed at all. That clue is gravity. Dark matter halos warp the very fabric of spacetime around them, bending the paths of light from distant galaxies in a phenomenon called gravitational lensing. It's like looking at a street lamp through the ripples of a pond. The light distorts, revealing the presence of something massive yet unseen. Without this ghostly gravitational fingerprint, we'd have no way to detect these halos at all. But even with this cosmic breadcrumb trail, studying them is like trying to reconstruct an elephant by only feeling its shadow. The challenge doesn't end there. Because dark matter doesn't interact with ordinary matter the way stars and gas do. It doesn't clump or collide. Instead, it forms vast, diffuse clouds that envelop galaxies like an invisible glove, holding them together with an unseen grip. Picture a whirlpool in space where the water is invisible. You only know it's there because the leaves floating on the surface spiral inward. That's how dark matter halos work. They dictate the motion of stars and galaxies, yet slip through our detectors like smoke through a sieve. So why does this cosmic asymmetry exist? Why would the universe hide most of its matter in plain sight, just out of reach? Some theories suggest dark matter particles are simply too elusive, passing through ordinary matter like ghosts through walls. Others propose we're missing an entire chapter in the book of physics, one where gravity behaves differently on cosmic scales. But until we crack this first great mystery, the true nature of these invisible giants will remain one of the most profound puzzles in science. the cosmic ledger doesn't quite add up when it comes to dwarf galaxies. According to our best simulations of dark matter halos, a galaxy like the Milky Way should be surrounded by hundreds, maybe even thousands, of tiny satellite galaxies, each tethered by gravity to its massive halo. But when astronomers peer into the night sky, they only spot a few dozen at most. This glaring mismatch between prediction and observation is called the missing satellite problem, and it's one of the most stubborn cracks in our understanding of how dark matter structures the universe. So where did all those dwarf galaxies go? One possibility is that our simulations are simply too generous, that dark matter doesn't clump on small scales the way we thought. Enter warm dark matter, a hypothetical cousin to the more popular cold dark matter theory. Unlike its sluggish counterpart, warm dark matter would move faster in the early universe, smoothing out those tiny density fluctuations that should have birthed countless dwarf galaxies. It's like trying to build sandcastles in a stiff breeze. The smaller structures never quite hold together. But while this idea patches one hole, it risks tearing another. Warm dark matter struggles to explain the larger scale patterns we see in galaxy clusters. Then there's the chance we're just not seeing the full picture. Dwarf galaxies are notoriously faint, often hiding in the glare of their brighter siblings or cloaked behind veils of interstellar dust. Modern telescopes are only now uncovering some of these shy cosmic neighbors, like finding fireflies drowned out by city lights. Yet even as our tools improve, the numbers still fall short. Could these missing satellites have been torn apart by galactic tides long ago, leaving behind only streams of stars as cryptic tombstones? Or does the answer lie in something more radical, an overlooked quirk in how dark matter interacts with itself? The stakes couldn't be higher. If dark matter halos aren't spawning the expected swarm of dwarf galaxies, it might mean we've misunderstood their very essence. Perhaps they're not the simple, sluggish particles we've modeled for decades, but something far stranger, particles that bump and scatter like cosmic billiard balls or even decay over time. Every undetected dwarf galaxy is a silent challenge to the foundations of astrophysics, whispering that the universe's hidden architecture might be more complex and more mysterious than we ever imagined. Deep inside every dark matter halo, there's a battle raging, one that pits the cold, precise predictions of supercomputer simulations against the messy, unpredictable reality of telescope observations. The heart of this conflict, a simple question: what does the center of a dark matter halo actually look like? According to decades of cosmic modeling, these halos should have sharply peaked densities at their cores, regions so dense they're called cusps, where dark matter particles crowd together like fans at the front of a concert. But when astronomers study real galaxies, they find something far smoother, a gentle plateau-like cores where the dark matter seems almost evenly distributed. This mismatch isn't just a minor discrepancy, it's a full-blown crisis in our understanding of how dark matter behaves. The Cusp-Core problem cuts to the very foundation of modern astrophysics. If our simulations, built on meticulously tested theories of gravity and particle physics, keep predicting dense cusps that don't exist, then either we're missing something fundamental about dark matter, or we've misunderstood how galaxies evolve. Some scientists argue the answer lies in dark matter itself. What if these invisible particles aren't the solitary, non-interacting ghosts we've assumed? Enter self-interacting dark matter, a bold twist on the classic theory. Instead of passing through each other effortlessly, these particles could collide and scatter like billiard balls in a cosmic game. Over billions of years, those microscopic interactions would gradually erase the dense cusp, smoothing it into the gentle cores we observe. It's an elegant fix, but not the only one. Others point to the overlooked role of ordinary matter. Stars, gas, and supermassive black holes aren't just passive passengers in dark matter halos. They're active shapers, unleashing colossal bursts of energy that can sculpt the invisible scaffolding around them. When young galaxies undergo violent bursts of star formation, the resulting supernova explosions act like cosmic sandblasters, pushing dark matter outward and hollowing out the center. Even the erratic dance of a supermassive black hole lurching through the galactic core as it devours matter and send gravitational shockwaves through the halo, flattening the cusp into a core. This process, called baryonic feedback, might be the universe's way of erasing its own sharp edges. Yet for every solution, new questions emerge. If self-interacting dark matter is real, why don't we see its fingerprints in the bullet cluster, where colliding galaxies suggest dark matter barely interacts at all? And if baryonic feedback is the answer, why do some tiny, star-poor dwarf galaxies where feedback should be weak still show flat cores? The Cusp-Core controversy isn't just a technical debate. It's a tug-of-war between simplicity and complexity, between the universe as we model it and the universe as it actually is. Until we solve it, every dark matter halo hides a secret at its center, one that could rewrite the rules of the cosmos. There's a cosmic paradox lurking in the shadows of our best simulations, one where the mightiest dark matter halos somehow fail at the very job they're supposed to excel at. Astronomers call it the too big to fail problem, and it's shaking the foundations of our most trusted model of the universe. Here's the puzzle. Supercomputer recreations of dark matter halos predict vast numbers of massive subhalos, dense, heavyweight structures that should act as gravitational anchors for bright, thriving dwarf galaxies. But when we scan the skies, these cosmic behemoths are nowhere to be found. Instead, we find only faint, wispy dwarfs drifting in regions where our simulations insist there should be stellar metropolises. It's like expecting skyscrapers and finding empty parking lots instead. This isn't just a minor accounting error. The too big to fail problem strikes at the heart of lambda-cold dark matter cosmology, the reigning framework that's guided astrophysics for decades. If these simulated subhalos truly exist but remain empty, it implies dark matter behaves in ways we haven't accounted for. Perhaps their cores are less dense than predicted, making them unable to hold onto the gas needed to birth stars. Or maybe something violent, ancient galactic collisions or torrents of radiation from the early universe stripped these potential galaxies bare before they could shine. One provocative solution flips the script entirely. What if dark matter isn't completely cold and sluggish? Warm dark matter, moving faster in the primordial universe, could suppress the formation of these overgrown subhalos, bringing simulations closer to reality. Yet this fix comes with trade-offs. It risks erasing too many small structures, reigniting the missing satellites problem we thought we'd solved. Others suggest dark matter might interact with itself, exchanging energy like cosmic pool balls to soften those overinflated halos. Then there's the wild card baryonic physics, where ordinary matter fights back. Supernova explosions and ravenous black holes could have blasted away the gas in these halos, leaving them massive but dark. The implications ripple far beyond a few missing galaxies. If our simulations consistently overpredict the heft of dark matter subhalos, it might mean we're misjudging the universe's entire skeletal structure. Every tweak to explain this anomaly sends tremors through cosmology, forcing us to question whether lambda-cold dark matter is the final answer or just the best placeholder we've found so far. For now, these ghostly colossus halos stand as silent monuments to the gaps in our understanding, reminding us that the universe's hidden machinery is far more nuanced than any simulation can capture. Look up at the Milky Way's satellite galaxies, and you'll notice something strangely orderly for a universe ruled by chaos. Instead of scattered randomly around our galactic neighborhood like marbles tossed onto a floor, these dwarf galaxies cluster together in an unnervingly flat plane, a razor-thin disk that slices through the Milky Way at a precise angle. This isn't just a quirky coincidence, it's a full-blown anomaly called the plane of satellites problem, and it defies everything our simulations say dark matter halos should do. In a universe governed by gravity alone, satellite galaxies should swarm their host like bees around a hive, orbiting in all directions with no preferred alignment. That's the isotropic distribution predicted by Lambda called dark matter theory, where dark matter halos act as gravitational anchors for a chaotic, three-dimensional dance. Yet reality paints a different picture. Of the dozens of satellites orbiting the Milky Way, nearly half cling to this single, improbable plane, some even moving in sync like synchronized swimmers. The odds of this happening by chance, less than 1 in 1,000. So why does the cosmos seem to favor this cosmic conga line? One radical explanation suggests dark matter isn't the invisible puppeteer we thought. Could these satellite galaxies actually be tidal dwarfs born not from primordial dark matter clumps, but from violent collisions between ancient galaxies? When massive galaxies graze past each other, they can rip out streamers of gas and stars that later coalesce into new dwarf galaxies. Unlike dark matter-rich satellites, tidal dwarfs would inherit the motion of their parent galaxies, naturally aligning along a shared plane. It's a compelling idea, but there's a hitch. Most Milky Way satellites show signs of being far older than any recent galactic smash-up, their stars dating back nearly to the Big Bang. Others argue the plane is a fossil imprint of the Milky Way's formative years. Dark matter halos aren't featureless clouds, they're threaded with invisible filaments, cosmic highways where gas and galaxies flow. If our satellite galaxies were born along one of these primordial filaments, their shared trajectory might persist for billions of years, frozen in time like flies in amber. Yet even this elegant solution raises new questions. Why don't other galaxies, like Andromeda, show equally striking satellite planes? And how could such a delicate alignment survive eons of gravitational tugs from passing galaxies and dark matter substructure? The most unsettling possibility is that we've misjudged dark matter's fundamental nature. Modified gravity theories like MOND eliminate dark matter entirely, replacing it with tweaked laws of gravity that naturally produce satellite planes. But these alternatives struggle to explain other dark matter halo phenomena, from gravitational lensing to the bullet cluster. Meanwhile, cutting-edge simulations hint that certain self-interacting dark matter models might amplify the odds of satellite planes, though not nearly as vividly as we observe. Whether a statistical fluke or a cosmic clue, the plane of satellites stands as a quiet rebellion against our cleanest theories. It reminds us that the universe's hidden architecture might be far stranger and more structured than our simulations dare to suggest. Until we crack this celestial riddle, every aligned dwarf galaxy whispers that dark matter's story is still missing pivotal chapters. Some galaxies are cosmic illusions, seemingly fragile wisps of light that hide staggering gravitational secrets. Take Dragonfly 44, a galaxy so dim it was only discovered in 2015, blending into the background like a whisper in a thunderstorm. Despite emitting less than 1% of the Milky Way's light, this ultra-diffuse galaxy weighs as much as our own, its gravity betraying the presence of a monstrous dark matter halo. How can something so faint anchor something so massive? The answer appends everything we thought we knew about how galaxies are built. Conventional wisdom says galaxies grow from the inside out. Dark matter halos pull in gas, which forms stars which light up the cosmic night. But ultra-diffuse galaxies like Dragonfly 44 flout this rulebook. They're cosmic paradoxes, bloated with dark matter yet starved of stars, like ghost towns with the infrastructure of megacities. Some might assume these galaxies are just failed experiments, places where star formation sputtered out early, but their dark matter halos are too pristine, too perfectly preserved for that to be the whole story. If they'd collapsed under their own weight or been torn apart by galactic tides, their halos would show scars. Instead, they're eerily intact, as if they've always existed in this shadowy, half-finished state. One theory suggests these galaxies are cosmic fossils, relics from an era before the universe learned to make stars efficiently. In the early cosmos, dark matter halos may have formed faster than the gas could cool and condense, leaving vast reservoirs of invisible matter with almost nothing to illuminate them. Another idea points to extreme environments. Some ultra-diffuse galaxies orbit near galaxy clusters, where tidal forces could have stripped away their gas while leaving their dark matter halos untouched, like a tree stripped of leaves but still rooted deep. But Dragonfly 44 throws a wrench in even those explanations. It floats in near isolation, far from the gravitational violence of clusters, yet still somehow avoided forming stars in proportion to its dark matter. This forces astronomers to consider darker possibilities. Could certain dark matter halos be inherently inhospitable to star formation? Perhaps their particles interact in ways that heat gas or generate magnetic fields, preventing it from ever cooling into stars. Or maybe the real mystery isn't why these galaxies are so dim, but why galaxies like ours are so bright in comparison. The implications ripple far beyond a few oddball galaxies. If dark matter halos can exist in such stark isolation from the visible universe, it suggests a shocking disconnect between the two. Stars might be optional accessories rather than the main event, with dark matter calling the shots behind the scenes. Every ultra-diffuse galaxy is a challenge to the grand narrative of cosmic evolution, proving that the universe still has rules and exceptions we've yet to uncover. If dark matter halos are the unseen engines driving galaxy rotation, then something is wrong with the cosmic blueprints, because these engines appear to be spinning in ways that defy expectations. Computer models predict that dark matter halos should rotate with a specific pattern, their angular momentum building steadily from core to edge like a whirlpool gaining speed. Yet when astronomers measure real galaxies, they find stars and gas often spinning at odds with their halos' simulated motion. Some galaxies rotate too fast, others too slow, and some even spin perpendicular to their halos' predicted axes. This disconnect, known as the halo spin paradox, suggests a fundamental flaw in how we think dark matter governs galactic motion. At the heart of the paradox lies a simple question: who's leading the dance, the visible galaxy or its invisible halo? In theory, dark matter halos form first, their gravity drawing in gas that eventually cools into stars. As this gas settles, it should inherit the halo's spin, aligning like a figure skater pulling in their arms to rotate faster. But reality is messier. Some spiral galaxies, like the iconic whirlpool, spin much faster than their halos should allow, as if an unseen hand is pushing them. Others, like the ultra-diffuse galaxy NGC 1052, rotate barely at all despite residing in massive halos. Then there's the case of polar ring galaxies, where stellar orbits wrap around the halo's poles like a belt around a tilted waist, a geometry that simulations struggle to explain. Baryonic physics might hold part of the answer. When gas collapses to form stars, it doesn't just passively follow the halo's spin, it fights back. Supernova explosions can inject energy into the system, altering angular momentum like a pinwheel caught in a gust of wind. The chaotic feeding frenzies of supermassive black holes might also torque galactic disks, scrambling their original spin directions. Some researchers argue that mergers play an even bigger role. When two galaxies collide, their halos don't just merge. They engage in a gravitational tug of war that can completely reset the spin axis of the resulting galaxy, leaving it misaligned with its new halo. But baryons alone can't explain all the anomalies. That's led some theorists to reconsider dark matter itself. Could certain halo particles carry a subtle electromagnetic charge, allowing them to interact with magnetic fields and transfer angular momentum to visible matter? Or might dark matter halos be lumpier than simulations suggest, their uneven mass distributions creating torque that warps galaxy spins over time? The most radical proposals involve dark matter vortices swirling currents within halos that could focus angular momentum in unexpected ways, like cosmic whirlpools redirecting a river's flow. The halo spin paradox isn't just a technical hiccup, it's a window into the dynamic relationship between the seen and unseen universe. If dark matter halos and galaxies aren't spinning in lockstep, it implies their evolution is far more entwined than we assumed. Every misaligned galaxy is a clue hinting that dark matter might not be the silent partner we imagined, but an active participant in shaping the cosmic dance. Until we solve this puzzle, the true rhythm of the universe remains just out of sync. The Milky Way isn't just a swirling disk of stars, it might be hiding a shadowy twin buried within it. This is the dark disk hypothesis, a provocative idea suggesting our galaxy contains a second, invisible disk woven from dark matter, spinning in parallel with the stars we see. At first glance, it sounds like science fiction, but there's a compelling reason scientists take it seriously. Certain stars in our galaxy move too fast, as if tugged by something we can't see. Could this phantom structure explain why our cosmic neighborhood doesn't quite obey the rules? Evidence for a dark disk comes from subtle anomalies in the motion of nearby stars. Imagine throwing a pebble into a pond. The ripples you see depend on the water's depth and the pebble's weight. Similarly, the way stars orbit the Milky Way center should reflect the gravitational pull of the dark matter halo enveloping it. But some stars, especially those close to the galactic plane, zip around faster than expected, hinting at extra mass concentrated in a disk-like shape rather than the diffuse, spherical halo we've long assumed. One study even calculated that a thin, dark disk could account for these speed discrepancies if it contained about half the mass of the visible stellar disk, effectively doubling the Milky Way's hidden architecture. Not everyone's convinced, though. Skeptics argue these stellar speedsters could be explained by ordinary astrophysics like undetected gas clouds, spiral arm resonances, or even hiccups in our models of galactic dynamics. Others point to the lack of direct evidence. If a dark disk exists, why don't we see its gravitational imprint on other tracers, like globular clusters or distant satellite galaxies? Then there's the puzzle of how such a structure could form in the first place. Dark matter, by definition, doesn't collide or clump like gas and stars. For it to flatten into a disk, it would need some way to shed energy, much like a spinning cloud of gas cools and collapses. That would require dark matter to interact with itself or with ordinary matter in ways we've never observed. Yet if the dark disk is real, it could rewrite the playbook for dark matter detection. Most experiments, like those deep underground searching for rare particle collisions, assume dark matter is uniformly distributed in a vast halo. A dense, local disk would mean particles could be far more concentrated near Earth, boosting the odds of capture, or even explaining why past detectors have picked up ambiguous signals. Some theorists speculate this could be why certain experiments, like Dharma/Libra, claim seasonal fluctuations in dark matter hits as Earth's orbit carries it through a hypothetical dark disk. The debate highlights a deeper truth. Dark matter halos might not be the simple, featureless clouds we've modeled them as. They could harbor hidden structures, disks, streams, even knots that challenge our most basic assumptions. Whether the dark disk hypothesis holds up or not, it's a reminder that the universe's hidden layers are always more intricate than they appear. Every anomalous star motion is a potential clue, pointing toward a richer, messier cosmic story waiting to be unraveled. What if the answer to dark matter halos isn't more matter, but a rewrite of the laws of gravity themselves? That's the radical proposition behind modified Newtonian dynamics, or MOND, a theory that dares to challenge the existence of dark matter entirely. Instead of invoking invisible halos to explain why galaxies rotate faster than Newton's equations predict, MOND tweaks gravity itself, suggesting it behaves differently when tugged by the feather-light pull of distant stars. At first glance, it's an elegant fix, one that neatly matches the rotation curves of countless spiral galaxies without needing a single dark matter particle. But as with any cosmic shortcut, the devil lurks in the details. MOND's greatest triumph lies in its simplicity. Take a galaxy like the Milky Way. Its outer stars whirl around the center so fast that, by Newton's math, they should fly off into the void. Dark matter halos solve this by adding invisible mass to glue those stars in place. MOND achieves the same effect with a tiny adjustment. Below a certain minuscule acceleration threshold, gravity gains a subtle boost, as if space itself remembers to push a little harder on distant objects. This single tweak reproduces galaxy rotations with uncanny precision, even for galaxies where dark matter models struggle. Some researchers argue it's no coincidence that MOND's success hints at a deeper truth about how gravity operates on galactic scales. But the cosmos is a relentless fact-checker. For all its elegance, MOND stumbles when faced with the bullet cluster, a cosmic collision where galaxies and their dark matter halos appear to have been wrenched apart. X-ray observations show most ordinary matter lingering in the cluster's center, while gravitational lensing reveals mass, presumably dark matter floating far outside, as if it sailed through the crash unaffected. MOND struggles to explain this separation without invoking some form of invisible mass, effectively recreating the very problem it sought to erase. Worse, it fails to account for the intricate large-scale structure of the universe, the cosmic web of galaxies threaded along dark matter filaments that simulations like lambda-cold dark matter model so effortlessly. Yet MOND refuses to fade into obscurity. Recent refinements like relativistic extensions that bend Einstein's equations instead of Newton's aim to close these gaps. Some theorists even explore hybrid models where dark matter exists but plays second fiddle to modified gravity, a cosmic compromise that might explain why certain dwarf galaxies follow MOND predictions to the letter while others defy them. The debate often grows heated, with proponents on both sides accusing the other of ignoring inconvenient data. What makes this clash so compelling isn't just the science, it's the philosophical divide at its core. MOND forces us to question whether we've been too quick to fill the universe with invisible stuff, rather than questioning the rules we thought were set in stone. Every galaxy that spins too fast is a reminder that our understanding of gravity is built on earthly experiments, extrapolated across light years with unproven certainty. Whether MOND ultimately triumphs or falls, its legacy is secure. It proves that the universe's greatest mysteries demand not just answers, but the courage to rewrite the questions. Picture two dark matter halos with identical masses. One sprawls like a foggy nebula, its particles loosely bound and diffuse, while the other clings tightly to its center, dense and compact like a cosmic fist. This isn't just a quirk of galactic architecture, it's a full-blown mystery called the halo mass concentration tension, and it reveals a glaring rift between our simulations and the real universe. According to the rules of lambda-cold dark matter cosmology, lower mass halos should be less concentrated, their particles spread over larger volumes. Yet when astronomers peer at dwarf galaxies and low-mass clusters, they often find halos packing far more mass into their cores than our models allow. It's as if the universe played a prank on our simulations, cramming extra dark matter into places it shouldn't fit. The implications ripple far beyond a technical discrepancy. Halo concentration, how densely dark matter crowds toward the center, dictates everything from a galaxy's rotation speed to its resilience against tidal forces. Get this value wrong, and entire galactic histories unravel. Take the dwarf galaxy Draco. Its stars orbit at velocities suggesting a dark matter core far denser than any simulation predicted, as if its halo collapsed inward with unusual fervor. Meanwhile, some ultra-faint dwarfs exhibit concentrations so high they defy straightforward explanations, their halos seemingly frozen in a state our models reserve for the early cosmos. One leading theory points to baryonic feedback, the explosive influence of ordinary matter. When stars form and die in bursts, supernova can blast gas outward, dragging dark matter with them through gravity. In massive galaxies, this process typically hollows out halo cores, but in puny dwarfs, the math flips. Their weaker gravity might let feedback events increase concentration by pushing dark matter inward rather than outward, like squeezing a stress ball in one spot only to bulge another. Then there's the wild card of reionization, the epoch when the first stars flooded the universe with radiation. Early dwarfs bathed in this harsh light may have had their gas sterilized, stunting star formation and leaving their halos oddly pristine, their concentrations untouched by later astrophysical chaos. Others suspect the answer lies in the primordial universe. Dark matter halos inherit their blueprints from microscopic density fluctuations in the infant cosmos, quantum ripples stretched to cosmic scales by inflation. If those fluctuations weren't perfectly random, if certain patches of the early universe were marginally denser, they could have birthed halos with naturally higher concentrations, like bread dough with uneven pockets of yeast. Intriguingly, some modified dark matter models, like those with a dash of self-interaction or quantum wave-like properties, amplify these effects, creating halos that defy the standard mass-concentration relationship. But the plot thickens when we study galaxy clusters. Here, the tension sometimes reverses, with massive halos appearing less concentrated than simulations predict. Could this be a clue that concentration isn't just about initial conditions or feedback, but about a halo's entire life story? Mergers, tidal stripping, and even the cosmic web's gravitational tides might tweak halo density over time, leaving a patchwork of concentrations that no single rule can explain. The mass concentration tension isn't just a puzzle, it's a stress test for our understanding of dark matter's nature. Every over-concentrated dwarf galaxy whispers that halos might have memory, bearing imprints of their formation that transcend simple mass. Every under-concentrated cluster hints that dark matter's story is woven with threads we've yet to untangle. Until we solve this riddle, the true architecture of the cosmos remains half-hidden, its blueprints smudged by the very stuff meant to hold it together. Some dark matter halos are cosmic voids in disguise, massive, gravitationally potent structures that somehow host no stars, no galaxies, not even a wisp of visible matter. These are the empty halos, shadowy islands adrift in the cosmic ocean, and their existence poses a simple yet haunting question. Why does the universe build invisible palaces with no one to live in them? One possibility is that these halos are failed galaxies, places where the recipe for star-making went disastrously wrong. Imagine a dark matter halo forming in the early universe, its gravity pulling in vast clouds of hydrogen gas. But perhaps that gas was too hot, too turbulent, or too sparse to cool and collapse into stars. Without this critical step, the halo remains forever dark, a celestial stage set for a performance that never begins. Supporting this idea are observations of certain ultra-diffuse galaxies which cling to the edge of visibility, suggesting that halos can hover just shy of the star-forming threshold. If conditions had been slightly different, a touch more gas, a bit less heat, they might have lit up the cosmos. Instead, they linger as ghostly what-ifs. Then there's the chance we're simply missing the galaxies hidden inside these halos. Telescopes, even our most advanced ones, have their limits. Dwarf galaxies are notoriously faint, and if they're cloaked in dust or drowned out by brighter neighbors, they could easily evade detection. Some empty halos might actually host galaxies so dim they're practically invisible, like fireflies lost in the glare of a city. Recent surveys using ultra-sensitive instruments have already begun to unmask a few of these shy cosmic residents, suggesting our census of dark halos may be incomplete. But the plot thickens when we consider the role of environment. Halos floating near galaxy clusters face particularly brutal conditions. The gravitational tides from these dense, violent regions can strip away gas before it has a chance to form stars, leaving behind barren dark matter skeletons. Even worse, the intense radiation from nearby quasars and starburst galaxies can ionize gas in neighboring halos, sterilizing them before star formation can take root. It's cosmic sabotage on a grand-scale. Halos robbed of their stellar potential before they ever had a chance. Yet the emptiest halos might hold the most profound clues about dark matter itself. If certain halos remain dark not because of external forces but due to some intrinsic property of dark matter, perhaps an inability to clump on small scales or a faint interaction with ordinary particles, they could be the key to unlocking its true nature. Simulations of warm dark matter, for example, predict a surplus of low-mass halos devoid of galaxies, matching observations eerily well. Other theories, like fuzzy dark matter composed of ultralight quantum waves, might leave similar fingerprints. The enigma of empty halos forces us to confront an unsettling truth. The universe may be far richer in darkness than we ever imagined. For every glowing galaxy, there could be dozens of invisible counterparts, silent and unseen. They remind us that the cosmos doesn't owe us starlight, that dark matter halos, not galaxies, might be the universe's default state. Every barren halo is a question mark, challenging us to reconsider not just where galaxies form, but why they form at all. We've long imagined dark matter halos as perfect, featureless spheres, smooth cosmic cocoons enveloping galaxies in symmetrical silence. But the universe has a habit of defying our simplest assumptions. Recent observations reveal these halos as cosmic contortionists, stretching, flattening, and twisting into shapes far more complex than we ever predicted. Some resemble squashed soccer balls, others lopsided pears, and a few even take on eerily flattened disks. This isn't just a curiosity, it's a paradigm shift, forcing us to rethink how halos form, evolve, and sculpt the galaxies within them. Take tidal interactions, the cosmic tug-of-war that reshapes halos over billions of years. When galaxies collide or swing too close to a cluster's gravitational grip, their dark matter halos don't just pass through unscathed, they deform like taffy. The result, halos stretched into triaxial shapes with three unequal axes giving them a distinctly lopsided profile. The Milky Way's own halo might bear these scars, its outer edges warped by ancient encounters with the Large Magellanic Cloud. Simulations show these tidal forces can even flip a halo's orientation over time, leaving its axis tilted like a spinning top knocked off balance. But tidal stretching isn't the only sculptor. The very process of galaxy formation can mold halos from within. As gas collapses to form stars, it drags dark matter inward, compressing the halo's core into a denser, flatter shape like a balloon pressed between two hands. Meanwhile, the furious outflows from supernova and active galactic nuclei can punch cavities in the halo, creating asymmetries that persist for eons. The combined effect is a halo that's anything but spherical, its form a frozen record of the violence and chaos that shaped its history. These odd geometries have real consequences for dark matter hunters. If halos are lumpy or elongated, the local density of dark matter particles near Earth could vary wildly. Some detectors might sit in underdense voids, while others bask in unexpected hotspots. It's like trying to measure rainfall with cups placed randomly in a storm. Some catch deluges, others barely a drizzle. This could explain why certain experiments report conflicting signals, their results skewed by the invisible topography of our own halo. Even more intriguing are the halos that defy categorization entirely. Some ultra-diffuse galaxies float inside halos so flattened they're more frisbee than sphere. Others, like those in the Coma cluster, show halos stretched into filamentary tendrils, as if the dark matter itself is being woven into the cosmic web. Each aberration is a clue hinting that dark matter might interact with itself, or with gravity in ways we've yet to fathom. The takeaway is clear: dark matter halos are not the silent, static monoliths we once thought. They're dynamic, evolving entities, their shapes etched by eons of cosmic violence. Every deviation from the spherical ideal is a window into the unseen forces that govern the universe, and a reminder that the darkest corners of space are also the most surprising. Deep in the cosmos, brief flashes of radio energy flicker like cosmic Morse code fast radio bursts, or FRB, erupting with the power of hundreds of millions of suns in mere milliseconds. These enigmatic signals, traveling billions of light years, might hold an unexpected key to mapping the invisible architecture of dark matter halos. Here's how, as these bursts journey across the universe, they pass through the diffuse gas shrouding galaxies, their signals subtly distorted by the very matter we can't see. It's like using a flashlight in a foggy forest. The way the beam scatters reveals the shape and density of the mist. The potential is staggering. Dark matter halos are thought to be swathed in layers of hot, ionized gas, material too faint to detect directly, but which leaves fingerprints on passing FRBs. By analyzing how these bursts disperse and delay, astronomers could reconstruct the distribution of this hidden gas, effectively tracing the outline of the halo itself. Some teams have already tried using bursts like FRB 211105, which passed through multiple galaxies on its way to Earth. The data hints at variations in gas density that align eerily with predicted halo boundaries, as if the bursts are sketching the edges of an invisible hand. Yet skepticism lingers. FRBs are notoriously unpredictable, and their paths through halos are random, like trying to map a city by analyzing only the occasional car headlight. Without precise knowledge of a burst's original brightness or the exact path it traveled, separating the halo's influence from other cosmic interference becomes a game of statistical guesswork. Critics argue that until we can pinpoint FRB origins or observe thousands more, the technique remains more promise than proof. The breakthrough may lie in next-gen telescopes like the Square Kilometre Array, capable of catching hundreds of FRBs daily. With enough bursts, patterns could emerge, revealing not just halo shapes but their evolution over time. Imagine detecting halos stretching under tidal forces or spotting ghostly subhalos lurking in the voids, all through the whispers of radio waves. Some theorists even speculate that certain FRB anomalies, like unexpected scattering or polarization twists, might betray exotic dark matter interactions, turning these bursts into probes for particle physics itself. For now, the FRB halo connection remains a tantalizing what-if. But in a universe where darkness outweighs light, sometimes the brightest clues come from the briefest flashes. Every millisecond burst is a potential key waiting to unlock the secrets of the cosmic shadows. Simulations paint a universe teeming with dark matter subhalos, countless invisible islands swarming around galaxies like moths drawn to a flame. Yet when astronomers point telescopes at the night sky, they find far fewer satellite galaxies than these models predict. This glaring mismatch, known as the substructure crisis, forces a reckoning. Are our simulations fundamentally flawed, or does dark matter behave in ways we never anticipated? At the heart of the crisis lies a paradox of scale. Supercomputer models, like those based on lambda-cold dark matter cosmology, generate intricate cosmic webs where massive halos host thousands of smaller subhalos. These dense knots of dark matter should act as gravitational anchors for dwarf galaxies, littering space with stellar companions, but our cosmic neighborhood tells a different story. The Milky Way, for instance, has only about 60 known satellite galaxies, a fraction of the hundreds or even thousands predicted. Where did all those subhalos go? One camp argues the answer lies in the violent interplay between dark matter and ordinary matter. Subhalos aren't indestructible. They can be shredded by tidal forces or evaporated by the searing radiation from newborn stars. Picture a fragile sandcastle battered by waves, the smallest subhalos, lacking the gravitational muscle to hold onto gas, might have been erased eons ago by the torrents of energy unleashed during the Milky Way's fiery youth. Supporting this view are faint stellar streams crisscrossing our galaxy's outskirts, ghostly remnants of dwarfs torn apart long ago. If this destruction was widespread, it could explain the missing satellites without rewriting dark matter's rulebook. Yet skeptics point to outliers like the Fornax dwarf galaxy, which orbits perilously close to the Milky Way yet remains stubbornly intact. If tidal destruction were truly efficient, Fornax should have been reduced to starlight smears by now. Even more puzzling are too big to fail Subhalo's massive dark matter clumps that simulations suggest should host bright dwarfs, yet stand eerily empty. Their survival implies something else is at play, perhaps a fundamental quirk in dark matter's nature. That's where alternative theories ignite debate. Warm dark matter, composed of lighter, faster-moving particles, would suppress the formation of tiny subhalos, naturally thinning the herd. But this fix risks overcorrecting, erasing not just the excess subhalos but also those we actually observe. Other models propose dark matter with a faint ability to interact, its particles colliding like billiard balls to smooth out clumpiness over time. Then there's the radical idea of fuzzy dark matter, where quantum wave effects prevent subhalos from forming on small scales altogether. The stakes couldn't be higher. If subhalos are being destroyed, it means ordinary matter wields unprecedented power over dark structures, a dynamic we've barely begun to model. But if dark matter itself is more complex than we thought, it could upend decades of cosmological assumptions. Every undetected subhalo is a silent challenge, urging us to look deeper into the shadows. The answer might not just solve a simulation glitch, it could reveal an entirely new chapter in the story of the universe's hidden architecture. Drawing the edge of a dark matter halo is like trying to measure a cloud with a ruler. The boundaries blur into the cosmic background, leaving astronomers with a fundamental dilemma. Where does the halo actually end? Unlike planets or stars with crisp edges, these invisible structures fade gradually into the universe's scaffolding, their outer layers blending seamlessly with the filaments of the cosmic web. This ambiguity isn't just academic, it throws a wrench into how we weigh galaxies, map the universe's structure, and even define what constitutes a halo in the first place. Take the Milky Way's own dark matter halo. By convention, astronomers often define its edge as the radius where the halo's density drops to 200 times the universe's average matter density, a somewhat arbitrary line in the sand. But the reality is messier. Simulations show dark matter particles orbiting far beyond this boundary, tracing elongated paths that stretch hundreds of thousands of light years into intergalactic space. Some even loop back after journeys lasting billions of years, like cosmic boomerangs. This means a galaxy's true halo might be far larger and more interconnected than our textbooks suggest. The implications ripple across cosmology. Misjudging a halo's boundaries skews mass estimates, which in turn affects how we interpret gravitational lensing, galaxy rotation curves, and even the expansion rate of the universe. For instance, if the Andromeda galaxy's halo extends farther than we thought, its gravitational tug on the Milky Way could be stronger, accelerating our impending collision. Similarly, the missing baryon problem, where half the universe's ordinary matter remains unaccounted for, might hinge on these fuzzy edges. That absent matter could be hiding in the diffuse gas straddling the halo cosmic web boundary, too faint to detect but too massive to ignore. The boundary problem also challenges how we categorize cosmic structures. Is a wandering dark matter clump a satellite halo or just a kink in the cosmic web? Does a galaxy group sit inside a single mega halo, or are there individual halos merely touching? The answer could reshape our understanding of dark matter itself. Some theories, like fuzzy dark matter with its wave-like properties, predict halos that naturally blur into their surroundings, while others, like self-interacting dark matter, might produce sharper edges due to particle collisions. Perhaps the most tantalizing clue lies in the cosmic web's anatomy. Filaments, the universe's great dark matter highways, feed halos with a steady stream of matter, making their edges more like dynamic thresholds than fixed walls. Simulations reveal halos growing asymmetrically, with tendrils reaching out to grip nearby filaments, as if the universe itself struggles to tell where one structure ends and another begins. Every measurement, every simulation pushes us closer to a startling realization. Dark matter halos aren't isolated islands, but temporary knots in an ever-shifting cosmic net. The true boundary might not exist at all. Peering into the depths of cosmic history, astronomers have uncovered something unsettling: dark matter halos that defy the universe's natural rhythm. These primordial behemoths, detected lurking in the faint glow of galaxies barely a billion years after the Big Bang, appear shockingly mature, as if they skipped ahead in cosmic evolution. According to our best models, structures this massive shouldn't exist so early. It's like finding a skyscraper in a Neolithic village, a discovery that either means our construction timeline is wrong or the building blocks themselves are stranger than we imagined. The Lambda model, cosmology's gold standard, predicts a gradual growth for dark matter halos. Tiny quantum fluctuations in the infant universe should have taken hundreds of millions of years to snowball into the first gravitational anchors, with truly massive halos emerging much later. Yet observations tell a different story. The James Webb Space Telescope has spotted galaxies from the universe's toddler years, some as early as redshift 10, that shouldn't have enough dark matter to hold themselves together. Their halos seem to have assembled at breakneck speed, collapsing into existence faster than the laws of physics should allow. One explanation points to an overlooked player: baryonic matter. Perhaps the first stars and black holes weren't just passive residents of dark matter halos, they were active architects. Supermassive black holes feasting on gas could have unleashed torrents of energy, funneling dark matter into denser configurations through a process called dynamical friction. Think of it like a cosmic plow, carving furrows in the invisible substrate and accelerating its collapse. Similarly, violent bursts of star formation might have triggered shockwaves that compressed halos prematurely, jump-starting their growth. But baryons alone struggle to account for the sheer scale of these ancient anomalies. That's led some theorists to reconsider dark matter's fundamental properties. Cold dark matter, the cornerstone of lambdactum, moves sluggishly, clumping over eons. What if the early universe hosted a mix of cold and something else? Warm dark matter, with its lighter, faster-moving particles, could have formed halos more rapidly in the dense early cosmos. Alternatively, self-interacting dark matter might have clumped efficiently through particle collisions, like marbles gathering in a bowl. The most radical proposals ditch dark matter entirely. Modified gravity theories like MOND suggest these overgrown halos aren't halos at all, they're artifacts of gravity behaving differently when stretched across cosmic distances. But even MOND struggles to explain why these anomalies appear selectively, leaving other early galaxies seemingly on schedule. The paradox forces us to confront an uncomfortable truth: our cosmic clock might be misaligned. If halos grew faster than predicted, it could mean the universe's expansion history needs recalibrating, or that dark matter's role in the early cosmos was far more dynamic than we've assumed. Every ancient halo is a time capsule, holding clues to an era when the rules of structure formation were written in a language we're only beginning to decipher. Dark matter halos might be the cosmic architects, but they don't always build the same way. Picture two halos with nearly identical masses. One hosts a majestic spiral galaxy, its arms brimming with star-forming gas, while the other cradles an elliptical galaxy, a golden blob of ancient stars with barely a wisp of dust. This is the halo-galaxy mismatch, a puzzle that defies our simplest assumptions about how galaxies form. If dark matter halos truly govern cosmic structure, why don't they impose more order on the galaxies inside them? The answer might lie in chaos, specifically the messy, violent histories of galaxies themselves. Take the role of mergers, for example. When two galaxies collide, their halos merge into a single, more massive structure, but the fate of their stars and gas depends on the particulars of the crash. A head-on collision between gas-rich spirals can trigger a firestorm of star formation, exhausting the fuel and leaving behind a red and dead elliptical. Meanwhile, a gentler, off-center merger might preserve the spiral structure or even warp it into a ring galaxy. The same halo mass can thus produce wildly different outcomes sculpted by random cosmic accidents. Gas inflows add another layer of unpredictability. Halos act like cosmic conveyor belts, channeling gas from the intergalactic medium into their galaxies. But this process isn't always smooth. Turbulence, magnetic fields, and even feedback from supernova or black holes can disrupt the flow, starving some galaxies of fuel while flooding others. Consider the striking contrast between the Andromeda Galaxy, with its bustling star-forming regions, and its neighbor M33, a smaller spiral with a quieter stellar nursery. Their halos are similar in scale, yet their evolutionary paths diverged billions of years ago, thanks to quirks in their gas supply. Then there's the wild card of stochastic processes, tiny, random fluctuations that snowball into galactic destiny. A slight overdensity of gas here, a chance encounter with a smaller galaxy there, even the timing of a supernova explosion can tip the scales. Dwarf galaxies are especially prone to this chaos. Some, like the Large Magellanic Cloud, blaze with young stars, while others, like Draco, are fossilized relics of the early universe. Their halos are nearly twins, but their appearances couldn't be more different. This mismatch forces astronomers to rethink the halo-galaxy relationship. Perhaps dark matter halos are less like strict blueprints and more like cosmic stagehands setting the conditions, but leaving the performance to the whims of ordinary matter. The universe, it seems, has a flair for improvisation, turning the same invisible scaffolding into a dazzling variety of galactic forms. Every mismatched pair is a reminder that the cosmos thrives on surprises, weaving complexity into the fabric of the dark. Dark matter halos aren't just defined by their mass or shape. Some appear to simmer at different cosmic temperatures, revealing yet another layer of mystery in their hidden dynamics. This temperature anomaly isn't about heat in the traditional sense. It's a metaphor for how wildly the motions of stars and gas vary from one halo to another. In some galaxies, stars orbit at frenetic, chaotic speeds as if the halo is hot, while in others they glide smoothly like skaters on a frozen pond, suggesting a cold halo. These thermal fingerprints shouldn't differ so drastically if dark matter were uniform. So what's cooking or freezing these invisible structures? One clue lies in a halo's accretion history, the cosmic buffet of matter it's consumed over billions of years. Picture two halos born with identical mass. One grows slowly, nibbling on small clumps of gas and dwarf galaxies, while the other gorges on massive mergers, each collision sending shockwaves through its dark matter. The latter ends up heated, its particles stirred into a frenzy by the gravitational turmoil, like a pot of water boiling over. This might explain why galaxies in cluster environments, where mergers run rampant, often exhibit hotter halos than their isolated counterparts. But the story isn't that simple. Some pristine dwarf galaxies, far from any cosmic collisions, still show unexpectedly warm kinematics, as if their halos were born restless. Then there's the dark matter itself. If halos are warmer or colder than expected, it might hint at unseen properties of the particles that compose them. Cold dark matter, the reigning theory, assumes particles move sluggishly, naturally settling into cool, ordered halos. But what if some dark matter carries a whisper of interaction, not enough to collide, but enough to exchange energy like distant neighbors whispering in a crowded room? Even faint self-interactions could gradually heat a halo over time, explaining why certain galaxies defy temperature predictions. Alternatively, dark matter might come in multiple flavors, with a mix of fast-moving warm particles and slower cold ones, creating a spectrum of halo temperatures. The stakes go beyond mere classification. Halo temperature dictates how galaxies evolve. A hot halo's turbulent gravity can stifle star formation by preventing gas from cooling, leaving galaxies dim and gas-poor. Meanwhile, a cold halo's gentle embrace might let gas settle into serene disks, birthing spirals like the Milky Way. If we can decode this thermal puzzle, we'd unlock a new dimension of galactic destiny, one where the invisible hand of dark matter doesn't just build galaxies but sets their very rhythm. Every anomalous star's motion is a clue pointing toward a deeper truth. Dark matter halos aren't just passive scaffolds. They're dynamic, evolving entities, their hidden thermodynamics shaping the visible universe in ways we're only beginning to fathom. Stretching across the cosmos, dark matter halos may not be the solitary islands we once imagined. Some appear to point toward the universe's emptiest regions like cosmic compass needles. This bizarre phenomenon, known as the halo void alignment, reveals an eerie pattern. The elongated axes of halos often orient themselves perpendicular to nearby cosmic voids, those vast galaxy-poor bubbles that span hundreds of millions of light years. It's as if the invisible scaffolding of the universe is subtly responding to the gravitational whispers of nothingness itself. The implications are profound. In a universe governed solely by random chance, halo orientations should scatter like tossed straws, with no preferred direction relative to voids. Yet multiple surveys, from the Sloan Digital Sky Survey to cutting-edge hydrodynamic simulations, show halos consistently tilting away from these empty regions, like trees leaning in a persistent wind. One study even found that massive halos align more strongly, their shapes bending to the void's influence as if tugged by unseen strings. The odds of this happening by coincidence? Less than 1 in 10,000. So what's behind this cosmic choreography? One camp argues it's a fossil imprint of the early universe. During inflation, quantum fluctuations stretched into vast density waves, with overdense regions collapsing into halos while underdense ones ballooned into voids. If those primordial ripples carried a preferred direction like wrinkles in a stretched sheet, halos might inherit a lingering alignment to the voids they were born beside. It's a cosmic memory written in the language of gravity, preserved for billions of years. Others suspect dark matter itself holds the key. If dark particles interact weakly, not just with ordinary matter but with each other, they might collectively flow along the cosmic web's filaments, causing halos to deform in response to the void's gravitational pull. Picture a river carving a canyon. Over eons, even faint forces can sculpt something monumental. Intriguingly, certain self-interacting dark matter models predict exactly this kind of large-scale coherence, with halos naturally aligning to the void's tidal forces like iron filings to a magnet. But skeptics caution against overinterpreting the data. Could these alignments be illusions, artifacts of how we map the cosmic web? Voids aren't perfect spheres. They're irregular, often interconnected, making it tricky to define their true edges. If we've misjudged their shapes, the apparent alignment might vanish under closer scrutiny. Another wrinkle: galaxies within halos don't always share their host's orientation, suggesting baryonic physics, like gas dynamics or magnetic fields, might scramble the signal. The most tantalizing possibility is that halo-void alignment hints at gravity itself behaving differently on cosmic scales. Modified gravity theories like MOND struggle to explain the phenomenon without dark matter, yet they can't fully dismiss it either. If the alignment persists as surveys improve, it could force a rethink of both dark matter and gravity, a rare clue that the universe's hidden rules might be written in the silence of the void. Every halo turned toward the abyss is a question. Are we seeing the ghostly hand of dark matter's hidden interactions, or the echo of a primordial universe more structured than we dared to guess? The answer might lie not in the bright knots of galaxies, but in the dark, empty spaces between them. Dark matter halos might seem like silent architects, but their evolution is anything but static. It's locked in a cosmic tug of war with the very galaxies they cradle. This feedback loop, driven by supernova explosions and the ravenous appetites of supermassive black holes, blurs the line between cause and effect. Does the halo shape the galaxy, or does the galaxy reshape its halo? The answer isn't just unclear, it's rewriting our understanding of cosmic co-evolution. Consider a massive star reaching the end of its life. When it explodes as a supernova, the blast doesn't just light up the cosmos, it sends shockwaves rippling through the surrounding gas, heating it to millions of degrees and blasting it outward. This fury doesn't stop at the visible galaxy, it punches into the dark matter halo itself. As the gas surges outward, its gravitational pull drags dark matter along, hollowing out the halo's core like a spoon scooping the center of a melon. Over time, repeated bursts of stellar violence can transform a dense, cuspy halo into one with a flattened core, smoothing what simulations predict should be a sharp peak. But the real wildcard lies in the heart of galaxies' active galactic nuclei, or AN. When supermassive black holes feed, they don't just consume, they retaliate. Swirling disks of infalling matter generate jets of energy so powerful they can eject gas at nearly the speed of light, carving vast cavities in the surrounding halo. These outbursts don't just push gas around, they alter the very gravitational landscape of the halo, redistributing dark matter in ways that defy cold, collisionless models. Some simulations suggest AGN feedback might even heat dark matter particles, causing them to migrate outward and further dilute the halo's core, a process akin to stirring honey into tea until it dissolves. The paradox emerges when we ask which came first, the halo's structure or the galaxy's fury. A dense halo might funnel gas efficiently toward the center, fueling starbursts and black hole growth, which then erode the halo's core. But a pre-existing core might also determine how feedback propagates, like sound echoing differently in a cave versus a cathedral. Observations of low surface brightness galaxies add to the confusion. Some show flat cores but lack the star formation or AGN activity needed to carve them, while others, bristling with supernova, retain surprisingly dense halo centers. It's as if the rules of engagement change from one galaxy to the next. Unraveling this feedback loop is like trying to solve a puzzle where every piece reshapes itself as you touch it. Current simulations struggle because baryonic physics, the messy, chaotic behavior of ordinary matter, is notoriously hard to model at cosmic scales. Tiny tweaks to gas cooling rates or black hole accretion efficiencies can flip a simulated galaxy from chord to cuspy, or vice versa. Even the timing of feedback matters. An early AGN outburst might preemptively stifle star formation, leaving the halo pristine, while delayed feedback could amplify core erosion. The result, a spectrum of halo-galaxy relationships that no single model can yet explain. This isn't just academic nuance. The feedback loop holds clues to some of cosmology's biggest mysteries. If AGN and supernova can reshape halos, it might explain why some dwarf galaxies have unexpectedly diffuse cores, or why massive ellipticals show such very dark matter profiles. It could even hint at dark matter's particle properties, whether it interacts faintly with itself or responds to gravitational tides in ways we've yet to quantify. Every galaxy is a living experiment, its halo a palimpsest of countless feedback events, each layer overwriting the last. Until we decode this dynamic dialogue, the true story of cosmic structure will remain half-told, its pages scrawled in the invisible ink of dark matter. Dark matter halos are often seen as cosmic constants, silent and unchanging across the eons, but the universe has a way of subverting our simplest assumptions. When astronomers trace the growth of these halos over billions of years, they uncover a puzzling mismatch. Some appear to evolve far slower or faster than our simulations predict, as if dark matter itself is transforming in ways we never anticipated. This isn't just a minor glitch in the models, it's a fundamental riddle about whether the invisible scaffolding of the cosmos is as eternal as we've assumed. Take the halos anchoring massive galaxy clusters. According to lambda cold dark matter cosmology, these behemoths should grow steadily over time, their gravity pulling in more matter like snowballs rolling downhill. Yet observations of distant clusters, those fossilized snapshots of the early universe, reveal halos that are already shockingly mature, their masses nearly as hefty as their modern counterparts. It's as if they hit the cosmic gym early and then stopped working out, defying the gradual growth our simulations insist should happen. Even stranger, some low-mass halos seem to stall entirely, their growth stunted for reasons no one can yet explain. The implications are profound. If dark matter halos aren't evolving as expected, it could mean their particles aren't the passive, unchanging entities we've assumed. One provocative idea is that dark matter decays over time, its particles slowly disintegrating into lighter, less massive forms. Picture an invisible hourglass, its sands of dark matter quietly draining away over billions of years. This decay would subtly reduce a halo's gravitational pull, potentially explaining why some structures seem to plateau in their growth. Supporting this are hints from certain dwarf galaxies, whose stars orbit as if their halos have mysteriously shed mass over time. Another possibility is that dark matter interacts with itself, or with other forces in ways that become more pronounced over cosmic epochs. Perhaps early halos formed in a dense, hot universe where particles collided frequently, creating tightly bound cores. As the cosmos expanded and cooled, these interactions might have weakened, slowing later growth. Alternatively, dark matter could be influenced by an as yet undetected field similar to how dark energy accelerates the universe's expansion, that gradually alters its behavior. The most radical theories propose that dark matter isn't one substance but many, with different components dominating at different times. Early halos might have been rich in a fast-moving, hot variety that seeded rapid growth, while later epochs favored slower, cold particles that built structure more methodically. This cosmic handoff could create the illusion of stalled evolution when, in reality, we're seeing the transition between two dark matter eras. Yet every explanation faces stubborn contradictions. If dark matter decays, why don't we see its byproducts in our detectors? If it interacts, why do colliding galaxy clusters show halos passing through each other like ghosts? The halo time evolution riddle forces us to confront an unsettling truth. Dark matter might not be the static backdrop we've imagined, but an active, evolving player in the cosmic drama. Every mismatch between simulations and observations is a clue, hinting that the universe's hidden half has a life story we're only beginning to read. Dark matter halos and dark energy might seem like cosmic strangers, one sculpting galaxies, the other hurling them apart, but their invisible dance could hold the key to the universe's ultimate fate. While dark matter's gravity pulls halos together, dark energy's repulsive force stretches space itself, accelerating the expansion of the cosmos. This raises a tantalizing question. Could the properties of halos, their shapes, distributions, even their evolution carry hidden imprints of dark energy's influence? The answer might rewrite our understanding of both phenomena. Take the way halos cluster across the universe. In regions where dark energy dominates, its push against gravity should leave halos more sparsely distributed, like islands scattered by a rising tide. Yet surveys reveal subtle anomalies. Halos in some voids appear slightly denser or more elongated than expected, as if dark energy's grip isn't uniform. One theory suggests dark energy interacts weakly with dark matter, creating faint pressure that nudges halos into unexpected configurations. It's a cosmic tug of war where the rope itself is stretching, complicating the struggle between collapse and expansion. Then there's timing. Dark energy's influence surged about 5 billion years ago, yet some ancient halos seem to bear scars of that transition. distant galaxy clusters, observed as they were when the universe was half its current age, show halo shapes that align oddly with the direction of cosmic expansion, like trees bent by a prevailing wind. Could this be evidence of dark energy's early stirrings, subtly warping halos before it overwhelmed gravity? Simulations that tweak dark energy's strength or evolution produce halos with skewed distributions, hinting that real-world anomalies might encode clues about this enigmatic force. The most radical idea, dark energy isn't a constant but a field that fluctuates, and halos might be its unwitting historians. If dark energy's strength varied across cosmic epochs, halos growing during lulls could differ from those forged in eras of fiercer repulsion. Halos in our local universe might retain a memory of these shifts, their masses or density profiles acting like fossils of dark energy's past behavior. Some theorists even speculate that certain ultra-diffuse galaxies, halos starved of stars, could be artifacts of dark energy's localized surges, their gas ripped away by sudden bursts of cosmic expansion. Yet skeptics caution against overinterpreting correlations. Halos are messy, shaped by mergers, feedback, and chaos that could mimic dark energy's fingerprints. The real test may lie in future surveys like Euclid or the Vera Rubin Observatory, which will map millions of halos with unprecedented precision. If their distributions or shapes deviate from lambda cold dark matter predictions in ways that align with dark energy models, it could forge the first tangible link between these two pillars of modern cosmology. The stakes couldn't be higher. Dark energy dictates the universe's destiny, whether it will tear itself apart or fade into cold oblivion. If halos harbor even faint traces of this force's nature, they're not just relics of structure, but prophets of the cosmos's final act. Every anomalous halo, every skewed alignment, is a silent message from the dark, waiting to be decoded. Deep beneath mountains and abandoned gold mines, scientists have built the universe's most sensitive traps, not for rare animals, but for the elusive particles that might make up dark matter halos. Experiments like LUX and Xenon operate in near-total darkness, shielded from cosmic rays by tons of rock and layers of ultra-pure water. Their detectors waiting for the faintest flicker of a collision between ordinary atoms and a passing dark matter particle. For decades, the prime suspect has been WIMP, or weakly interacting massive particles, theoretical heavyweights that fit neatly into existing physics. Yet after years of hunting, these detectors remain eerily silent. Every null result isn't just a setback, it's a revolution in the making, forcing us to ask, if not WIMP, then what? The stakes couldn't be higher. Identifying dark matter's particle would crack open the halo mystery, revealing why these structures dominate the cosmos yet vanish in our labs. WIMP once seemed inevitable. Their mass and weak interactions perfectly explained halo formation while slipping neatly into supersymmetry, a beloved extension of the standard model. But as detector sensitivity improved by orders of magnitude with no definitive signal, the mood shifted. Some researchers now compare the search to a high-stakes game of cosmic whack-a-mole. Each time one theory is ruled out, another, stranger candidate pops up. Enter axions, ghostly lightweight particles originally proposed to solve a totally unrelated puzzle in quantum physics. Unlike WIMP, which bulldozed through detectors like bowling balls, axions would interact so delicately they'd leave whispers rather than thuds. Experiments like ADMS hunt them not with liquid xenon, but with powerful magnetic fields designed to convert axions into faint microwave signals. The twist: axion halos might behave differently than WIMP halos, clumping in ways that alter galactic rotation curves or lensing patterns. If found, they'd rewrite the dark matter playbook entirely. Then there are sterile neutrinos, the elusive cousins of ordinary neutrinos, with just enough mass to shape halos but so reluctant to interact they make WIMP look sociable. Unlike WIMP or axions, sterile neutrinos could decay, emitting X-rays that telescopes might spot trailing from galaxy clusters. Some researchers claim hints of these X-ray signatures in stacked observations, though critics argue the signals blur into statistical noise. The hunt's urgency goes beyond curiosity. If dark matter particles interact even faintly beyond gravity, future detectors could map halos in unprecedented detail, not just their bulk mass, but their substructure, temperature, even their cosmic history. Picture a telescope that sees not light, but the invisible currents of dark matter itself. Conversely, if every search comes up empty, we may face a radical possibility. Dark matter isn't particulate at all, but something more exotic, like primordial black holes or flaws in spacetime's fabric. For now, every quiet detector deep underground is a message from the halos themselves, a reminder that the universe's greatest structures are built from stuff that refuses to follow our rules. Whether WIMP, axions, or something entirely unforeseen, the answer won't just solve a puzzle. It will redefine reality's blueprint. When black holes collide, the universe trembles, ripples in spacetime radiate outward, detectable by instruments like LIGO as gravitational waves. But dark matter halos merge constantly in the cosmic dance, their combined masses dwarfing even the most massive black holes. So why haven't we caught a single gravitational whisper from these colossal encounters? The silence is deafening, and the implications could reshape our understanding of both dark matter and gravity itself. The puzzle begins with scale. Unlike black hole mergers, which pack immense mass into compact volumes, dark matter halos are diffuse giants. Imagine comparing the splash of a pebble dropped into a pond to the barely perceptible swell of an entire lake. Tilting one creates sharp, detectable waves, the other a subtle shift too spread out to measure. Halos merge over hundreds of millions of years, their gravitational signals stretched into a faint, low-frequency hum that slips below LIGO detection threshold. Current observatories are tuned to catch the high-frequency chirps of stellar mass collisions, not the slow-motion mergers of invisible giants, yet frequency isn't the only hurdle. Gravitational waves are born from accelerating masses, and here's the twist. Dark matter might not accelerate the way ordinary matter does. Black holes plunge toward each other, their orbits tightening as they radiate energy. But if dark matter particles don't collide or experience friction, halos could simply pass through one another like ghosts in the night, their gravitational waves vanishingly weak. Simulations suggest only the densest core regions might emit detectable signals, if they exist at all. The Cusp-Core controversy rears its head again. If halos lack dense centers, their mergers could be nearly silent. This isn't just a technical challenge, it's a philosophical rift. Some theorists argue the absence of halo gravitational waves supports modified gravity theories, where dark matter doesn't exist and mergers follow different rules. Others propose more exotic solutions. Perhaps dark matter interacts via unknown forces, creating dark photons or other carriers that alter wave emission. Or maybe the signals are there, hiding in LIGO noise, waiting for advanced algorithms to tease them out. The next generation of observatories could break the stalemate. Space-based detectors like LISA will open a new window on low-frequency gravitational waves, potentially sensitive to the stately mergers of galaxy clusters. Pulsar timing arrays, which monitor the precise flicker of distant neutron stars, might catch the background rumble of countless halo collisions stretching back to the cosmic dawn. If any of these efforts bear fruit, we'll gain more than just confirmation of halos. We'll unlock a new way to map the universe's invisible architecture. Until then, the silence speaks volumes, reminding us that the darkest corners of space still hold their secrets tight. What if our universe's dark matter halos are just one variation in an infinite cosmic library, where every possible version of these invisible structures exists somewhere in the multiverse? This is the multiverse halo hypothesis, a speculative leap that ties the mysteries of dark matter to the wildest frontiers of theoretical physics. While firmly in the realm of unproven ideas, the notion isn't pure fantasy. It emerges naturally from inflationary cosmology, which suggests our universe is one bubble among countless others, each with its own unique physics. Imagine a cosmic kaleidoscope where every twist spawns a new universe, some with halos so dense they crush galaxies into oblivion, others so wispy they let stars scatter like dust in the wind. The logic hinges on inflation's aftermath. In the chaotic moments after the Big Bang, quantum fluctuations could have frozen into different configurations across separate universes, tweaking fundamental constants, including the properties of dark matter. Halos in one universe might be forged from cold, sluggish particles, while another's could be built from fast-moving, self-interacting variants. Some universes might lack dark matter entirely, their galaxies spinning wildly out of control. Others could be so saturated with it that their halos collapse into black holes before stars ever ignite. The staggering diversity arises from a simple question. If the multiverse is real, why wouldn't its halos vary as wildly as its laws? This speculative framework even offers a curious solution to the anthropic principle. The idea that our universe's laws appear fine-tuned for life because only such a universe could produce observers to notice them. If halos are too massive, galaxies fragment before life arises. If too weak, structures never coalesce. Our universe's halos, then, might be just right, not because of some cosmic accident, but because we're here to witness them. It's the Goldilocks effect writ large. In an infinite multiverse, every halo configuration exists, but only a tiny fraction permit the emergence of sentient beings to ponder them. Critics rightly dismiss this as untestable conjecture for now. Without a way to peer beyond our cosmic horizon, the multiverse remains a metaphysical playground. Yet subtle hints might lurk in our own universe. If inflationary theory predicts certain statistical patterns in halo distributions, say, an unexpected clustering of masses or shapes, those anomalies could echo the influence of neighboring universes. Some theorists even propose that collisions between bubble universes might leave scars in the cosmic microwave background, though current data shows no such marks. The most tantalizing version of this idea ties dark matter to string theory's landscape, where countless vacuum states correspond to different universes. In this view, halos aren't just structures, they're signatures of which universe we happen to inhabit. They're properties encoded with clues about the broader multiverse. It's a long shot, but so was the idea of an expanding universe a century ago. Until we crack dark matter's code, the multiverse halo hypothesis remains a reminder. The answers we seek might not just lie in the shadows of our cosmos, but in the infinite reflections of realities beyond. From the ghostly absence of dwarf galaxies to the perplexing spins of cosmic giants, dark matter halos have unveiled 25 mind-bending mysteries that challenge everything we think we know about the universe. These invisible titans dictate the fate of galaxies yet refuse to play by the rules, vanishing from our detectors, warping into unexpected shapes, and even appearing to evolve out of sync with time itself. Each discovery peels back another layer of the cosmic onion, revealing not just gaps in our knowledge, but entire chasms waiting to be crossed. Consider how far we've come and how much further we have to go. Just decades ago, dark matter was a fringe idea. Now we know it's the universe's hidden architect, its halos weaving the tapestry of reality itself. Yet for every question answered, why galaxies rotate too fast, how clusters hold together, dozens more erupt in its place. Why do some halos stagnate while others race ahead? What sculpts their bizarre alignments with cosmic voids? And perhaps most haunting of all, if dark matter truly makes up 85% of the universe's matter, why does it remain so agonizingly out of reach? The next chapter of this cosmic detective story is already being written. Telescopes like JWST are probing the ancient universe, hunting for baby halos in the cosmic dawn to see if they grew too fast too soon. The upcoming LISA mission could catch gravitational whispers from halo mergers, revealing whether these structures collide like titans or slip through each other like specters. Meanwhile, next-generation detectors buried deep underground continue their relentless search for dark matter particles, from axions to WIMP to theoretical wildcards we've yet to imagine. But here's the thrilling part: you don't need a PhD to be part of this revolution. Every time you look up at the night sky, you're gazing into the greatest unsolved mystery of all, a universe where darkness isn't the absence of light, but the canvas on which reality is painted. The answers are out there, hidden in the halos, waiting for the next curious mind to connect the dots. So stay wondering, stay awestruck, and most of all, stay tuned, because the cosmos always has another surprise up its sleeve.